Hello everyone, we'll wait for 5 minutes for everyone to join and then we'll start today's live session for the administration special concrete. So we'll start our class around 6:05. So hello everyone, myself Umesh Holi, I'm a PMRFT for the course administration special concrete. Today we will see the content of week 8 for the live session. So the week 8 content is divided into the subpart where we will still study some properties of agricultural ashes and how they are produced. Like for example, we will study sugarcane ash and what is their properties like reactivity and how we can make it as commercially viable solution to make it as a replacement for cement to make it as a SCM, and what are their disadvantages, and also we will see like what are the precaution has to be taken care when we use such ashes. Also, we will see assess some properties of rice husk ash and their microstructural properties and how they influence the cement hydration. Then we will see some of the results from calorimetry. Then we will analyze the post solution from this assay, and also we will see some study on the cache analysis in blender systems and life cycle assessment analysis. Also, we will see how they make cement eco-friendly or maybe less CO2 embedding by using this type of ashes. And furthermore on that, we will study life cycle assessment of a concrete. Yes. So the going forward with the question number one is simple question, which is on the which process most contributes to CO2 emission in the modern cement manufacturing, right? This question is asked because we want to study the life cycle cost analysis, and we know that cement is a product produces 8% of CO2 emission worldwide. Uh, but what is that which we can't avoid in the cement, and what is that which is leading to the maximum contribution of cement, maximum contribution of CO2 emission is the question asked. The first question is raw material of transport, because transportation of lead to use of heavy vehicles which can generate CO2 by exhaust from these vehicles which we required in abundant to transport the material like clays and also limestone to make the cement at the cement plant. The first question is regarding that. The second question is clinker formation itself. After taking the raw material, when we feed this to the clinkering process, the calcination takes place, which is at the elevated temperature. By that, as there is a increase in CO2 or the cement milling. After the clinkerization, we will mill it to make it fine. So obviously, the more amount of energy is required to mill it and to make it a very fine material. So the option number C is cement milling. Will it contribute to CO2 emission? Will is the predominant factor in contributing CO2 emission? And option number C is a gypsum blending. We will also, the last process of the cement production is to blend with the gypsum to reduce the problem of flash setting. So from this fourth option, which one is the more appropriate, which contribute most of the CO2 emission in the modern cement manufacturing? Take your time and you can type your answers in the chat box. Okay, let's see the answer for this question. As we know, the answer for this question is the B, clinker formation itself. The calcination reaction of formation of cement produces a lot of CO2 because of calcining it, because the limestone will break down and that will release the CO2 as a byproduct and forms the clinker. Hence, the reduction of the CO2 from the cement manufacture we can do by only using low clinker, like the typical clinker requirement of OPC system. We can reduce it by using the replacement such as the supplementary cementitious materials and try to lower down the use of clinker, because we need a clinker. Because of that only the hydration reaction will take place. So to eliminate that, uh, there is a way, or there's other ways like the geopolymers, which they use as the chemical activators to form the products by the reactions of geopolymerization. But also that this alkaline activators also have embodied energy in them, which could also to CO2 emission. Then you have to be very in a selection. You have to be carefully select a proportion of clinker in such a way that it is not producing a lot of CO2. So the next question is on what is the principal building compound developed early strength in the Portland cement. Let's say the Portland cement, a typical cement, there are some bulk compounds from which one of them is leading to a maximum or principal developing the early strength in the Portland cement. C3A, C3S, C2S, C4AF. This is a simple question, will not take much time here. We will move forward. The principal bulk compounds which leads to development of early strength in the Portland cement is C3S. So C3S is one of the leading for formation of early strength. Okay, this you can see the angular nature of the crystals, the angularity that can be C3S. This is more angular because and the more angularity will also promotes the more reaction, right? So that's why. So B. Okay. The next question is which reason best explains the PPC usually has lower carbon footprint than OPC. Just now we have studied that the production of OPC increases the CO2 concentration. So how to reduce that? And what is the PPC? PPC is a Portland pozzolana cement. And what is the main reason behind it lowering down the carbon footprint than the OPC? First question, the first answer for this question is the lower fineness of PPC. Yes, that could be the reason because the lower requirement of energy for making it fine, hence the lower CO2 footprint. The second option is utilization of industrial byproducts. Yes, that could also be one of the answer. Faster setting time, maybe not addition of extra line. Maybe we are adding extra line, so that's why we require lower clinker. That's why maybe the CO2 footprint of PPC will be lower than OPC. So the answer from this, most appropriate answer from this, try to answer. It will take some time, not more than 1 minute, and then we will see the answer. Anyone with the answer? Okay, let's see the answer for this question. The answer for this is utilization of industrial byproduct. As you know that PPC made up of fly ash. So fly ash is the byproduct from thermal power plant. So hence we can consider its CO2 footprint as 0. So as we know that the fly ash is the byproduct from thermal power plant which has the zero CO2 footprint. Then when we use in the OPC system to make it a PPC, then obviously the CO2 footprint will be reduced because we are replacing some of the part of OPC by fly ash, where we are considering their CO2 footprint is as zero. Only some CO2 footprint will be associated in transporting the fly ash from thermal power plant to a cement plant or a mixing plant or a grinding plant. That will not be that much. Hence, the main reason which best explains the PPC usually has a lower carbon footprint than OPC is utilization of industrial byproduct. Okay. Okay. The rice husk ash. Why does the porous silica structure result in a high surface area? The options are enhanced crystalline phases, trans heavy metals, maintains porosity even in the coarser grains, increase alkali content. So the porous structure lead to high surface area. Why? Okay, let's see the answer for this. So, so the maintain porosity even at coarser grains. They're asking, so why does the porous silica structure results in a high surface area? Yeah. So the properties of rhesus gas is having that it is having porous structures. So because of porous structures which is also present in the coastal grains, the overall surface area of rhesus gas is of very high magnitude compared to the other SCMs. Yes, because and you can see the structure also which looks porous. So the surface area increases because there is a area inside the structure also. Okay. Next question: what is the main consequence of excess carbon in SCBA used in cement? What is SCBA? Sugar cane bagasse ash. So when we burn the bagasse which is generated from sugar cane meals, the left out is of ash that is called as sugar cane bagasse ash. That is having some reactivity in it that we can use as a replacement and to make a cement, right? So option A is accelerated setting, loss of color, reduced photonic activity, high strength. What is the main consequence of excess carbon in SCBA used in cement? Also, we will study some of the consequences in the early setting characteristics. Excess carbon means there is a more organic compound, so which will hinder some of the properties early reactivity, or even it will be interacting with the superplastics as we use, so which could finally reduce in pozzolanic activity, right? Because there is no reactive silica present and most of this is excess carbon present which could hinder the pozzolanic activity and will not get the desired strengths. Okay. The next question is on which is which test monitor the cement setting by identifying the heat release during hydration. This is easy, will not take much time. Isothermal calorimetry, Lee chart roll, Wiccan needle, Blaine fineness. Obviously, everyone knows that Wiccan needle is used for initial setting, final setting time. Lee chart roll is used for unsoundness. Blame fineness is used for to calculate the fineness of cement. Obviously, isothermal calorimeter is the answer which is used to identify the heat release during hydration reaction, right? Heat release during hydration reaction, heat time. Okay. So the next question is on control burning of bagasse ash is mainly aimed at why we do control burning of bagasse ash. Just now we said that there is a problem of high organic compounds, which is carbon. Reducing particle size, reducing crystalline silica carbon content, enhancing alkali content, increase moisture level. So the answer is but obvious. Just now we have discussed that reducing crystalline silica and carbon content. By that way, we'll get good bagasse ash for the production of concrete using it as a SCM. What properties primarily limits the rice husk ash replacement level about 20% in the concrete. Oh, so there's a limit. So why there is that limit? As husk ash, we can't use more than 20%. So why there is a limit for that? The first option is excessive setting time, too much unreacted silica, high water demand, high shrinkage, low thermal stability. Take your time for this and then we'll move forward for the next question. Anybody with the answer? Okay, let's see the answer. So, the answer for this question is too much unreacted silica and high water demand because we know that the fineness and the surface area of the hibiscus is very high because of its coarse, like it's having more porous structure. Because of that, there is a high demand of water in it that can't be met, and too much unreacted silica. That's why we can't use more than 20% in concrete because it will take too much water. Okay. The next question is for which environment is sulfate resistant cement most suitable? We want sulfate resistant cement, obviously it should have sulfate resistance. Decorative flooring, marine structure, highway pavement, lightweight panels. which one will have the highest exposure of sulfates? But obviously, the exposure near to the sea, the coastal exposure will have sulfates coming from the sea water, hence marine structure should have a sulfate resistance. So what are some sulfate resistant cement which you guys know? Yes, slag based cements are good in sulfate resistance. Also, some of the new cements like CSAB cements and LC3 type of cement also show a better resistance against a sulfate attack, at least in the laboratory testing. Okay, so the next question is on which one of the following best promotes interactive discussion during the class. Sorry, this is not the question from the content we are studying today. Next question. Which indicator reflects the sustainability of concrete design? Which are those indicators which reflect the sustainability of the concrete? Apathy indexed, flashpoint, ratio of C3S to C2S, Blaine number. So this is a little tricky question, so we will not take much time and we'll study here the apathy index, which determine the how much CO2 emit per characteristics property with respect to durability or mechanical property. So, which defines the sustainability characteristics of the cement. Okay. So this index is used to characterize the sustainability of the concrete, like how much CO2 it is introducing, how much durability it is providing, how much cost is associated, etc. Next question is on what impact does high alkali content in ash have cement system on cement. Let's say now you have some ash, like for example from some industrial power plant or maybe from biomass ash, which is coming from agriculture residues. So if this is having the high amount of alkalis, then what will happen? First option, accelerates the pozzolanic reaction, may be true, because high alkalinity maybe creates the environment of high reaction and which will accelerate the pozzolanic reaction, may be true. Increases the risk of alkali aggregate reaction, ASR, alkali aggregate reaction could be possible. Improve color, decrease setting time, may be also possible, right? But the main disadvantages of having high alkali content is increasing the risk of alkali aggregate reaction. So we know that the aggregates are not reactive and they are inert material into the concrete. However, when there is an increase in alkalinity of these binders and in the post solution, they may react with the aggregate and lead to expansion stresses and lead to bursting, right? So that is not good for the concrete, and concrete will have durability issues when there is high amount of alkalis present. So hence we should always limit the amount of alkalis coming from the SCMs, right? Okay. How we can do that? There are some SCMs which promotes the binding of these alkalis also, or the hydration product. The nature of hydration product also influences the binding of alkalis, so which will not be easily available to react and to form ASR, right? So we can study those characteristics of alkalis and how they are reacting to the cement concrete. Okay. The next question is on which method best increases reactivity in the low grade fly ash for blended cement. Low grade fly ash we want. Which method? Grinding, leaching, washing, blending with calcium sulfate. How to increase the reactivity of fly ash? Let's say you have fly ash with you, or you are using, but you are not getting much reactivity. You want to increase the reactivity, but you don't want to invest a lot of energy in it. We know that the more the surface area, more the reactivity happens. So how to increase the surface area of fly ash? Can you think in that direction? Yes, of course. So if you can grind, which will lead to increase in a surface area. More surface area is available for reaction leads to more hydration product formation, lead to increase in reactivity. Correct. Okay. So the next question is, why does the LOI, loss on ignition of RHA, which is rice ash, rise at very high calcination temperature? You know that there is a temperature limit above which also if you go, there is an increase in loss of ignition. What will happen? What is happening at the high temperature in a rice cache? And do we need to provide that amount of high temperature? High potassium trapping unburned carbon, more moisture absorption, large particle size, high energy cooling. Let's see the answer. So at the high elevated temperature, higher potassium is trapped in unburned carbon. That's why there is a more loss of ignition. So that is also not desirable to have a very high temperature, which could lead to very high losses of ignition in RH. The next question is, which cement type generally has the lowest embedded energy per ton? So now this everyone should answer. Which cement type is having lowest embedded energy? Which is that cement which is producing lowest amount of CO2 into the environment? OPC, PSC, PPC, LC3. Take your time. Anyone with the answer? Okay, let's try to solve the answer. LC3. Why? Because in LC3 we have 45% replacement of clinker, right? Because which reduces the CO2 footprint drastically. Then there is a PSC. PSC also we replace by up to about 50%, which is slag, right? However, here the temperature requirement for production of this LC2 is lower. Okay, and then there is a but when we increases the PSC amount, the slag amount more than 50%, then the CO2 footprint of PSC will become even less than LC3. Fly ash also a similar case. If we increase a high amount of fly ash, then that will have lower CO2 emission. Because in LC3 we require LC to produce For LC2 production, there is some amount of heat is required, which also generates CO2, right? Okay. That's why this has to be carefully answered. However, the least one will have OPC, okay, because it's using a lot of clinker. Clinker produces CO2. Okay. The next question is on why. What does the initial setting time of cement indicates? Setting time what indicates? Final strength, start of solidification from plastic state, water absorption, maximum sinkage. This is very easy question, will not take much time. Start of solidification from plastic state is called as initial setting time. And can anybody tell how much is the initial setting time generally for the OPC type or any type of cement? It's around 30 minutes. And what is the final setting time? Final setting time. Final setting time around 10 hours. Okay. The next question is on what is the main advantages of white cement? Why we use white cement? Why there is a demand for white cement? Better sulfate resistance, decorative appearance, better alkali resistance, improve early hydration. Simple question, will not take much time here. The answer for this question is the cement, the white type of cement we use because it's having the decorative appearance properties. It is not that better sulfate resistance, not that better alkali resistance, not improves much hydration characteristics, but as in a decorative appearance, we can use a different type of colors with it. So that is most important from it. Okay. So for low heat concrete, which type of is preferred? Now we want to make a concrete which should have lower heat of hydration. How we can do it? We can use OPC, low heat cement, rapid hardening cement, quick setting cement. Oh, this is very. I would like to you to answer what type of material you will add into a particular amount to make it as a low heat concrete. Obviously, the answer is low heat cement. We will use low heat cement to make a low heat concrete. But how we can achieve is the question. Obviously, we will use SCMs in such a way that it reacts and forms the more CSS structures, right? So the use of fly ash. Use of fly ash is observed to reduce the heat of hydration produced by reaction of C3S, which is very reactive, as we have seen in the first question, where it's very highly reactive, which lead to the initial setting of the cement, which could produce a lot of heat of hydration in the initial stages. To lower down that, when we add a fly ash fly ash reacts with the byproduct from it is calcium hydroxide plus fly ash leads to formation of further CSH structures. So which will slower down some of the reactions of C3S, right? And in that way it reduces the heat generated. Okay. So where we will use this type of cement? Where there is a requirement of low heat concrete. Where is the requirement of low heat concrete? The application like mass concrete. Mass concreting, where it is the mass concrete is happening? like very big structures like rafts of buildings or maybe dams, right? So dams will have very high amount of volume of concrete. Because of that, it could generate a thermal stresses which could lead to cracking. So to eliminate that, we go for using the SCMs like a fly ash, which reduces the heat of hydration in the early stage. Next question is on a high alumina cement is mainly used for now. Where we generally use high alumina cement? Simple question. Underwater construction, heat resistant structures, decorative application. So the high amount of alumina is also called as refractory type of concrete, which is used at very heat resistant structures, for example furnaces, and the temperature where it goes very high, that location the high alumina cement is used. Where there is a little bit higher. Okay, let's move forward to the next question. What happens if the gypsum is omitted from the cement manufacturing? As we know that in a cement manufacturing, the last step is the grinding, and after that we will add gypsum, and again we will grind it to make it even finer. What if we eliminate the last process of gypsum addition? What will happen? Concrete will become more strong, or maybe flash set will happen. Improve workability can be possible. Early shrinkage. So answer is very easy. Answer is a flash set. If you don't have gypsum in our cement, then the reactions of other compounds is too fast, which could lead to a formation of a flash set, right? Because they will react very fast. There will be no space to further react, lead to flash set. To omit that, gypsum is added, which promotes the formation of yttriumite, and slowly there is a development of strength, and that reduces the possibility of flash set, right? So gypsum is also important. The next question is which phase is the main source of lead strength in hardened cement paste? Just we now seen that C3S is responsible for high early strength. High early strength, right? What is the compound which is responsible for late strength in hardened cement? Like after many years, we'll get that strength, which obviously the compound which is slowly reacting, and the slowly reacting compound we know that is C2S, which leads to ultimate increase in ultimate strength at the later age, right? Okay, and which also produces the low heat of hydration. That's why this type of cement should be used for the mass concreting, dam construction, where there is a requirement of reduction in the heat of hydration. Next question is on which is the direct consequences of clinker factor reduction in the blended cement. Blended cement, we are using the different type of SCMs in it to make it blended cement. What will happen? Direct factor, increase hydration of temperature, lowering of CO2, faster color change, lower plane fineness. What is the direct impact? Obviously, the direct impact is, now we have studied that it will reduces the CO2 emission, because we are reducing the most producing CO2 producing element from the cement, which is clinker. By that, a different type of blends are used, which are fly ash, slag, silica fume, rhesus ash, bagasse ash. We have studied till then, and also the new type of cement is called as LC2, limestone calcine clay. Yes, so by that way, we are eliminating the use of clinker. The next question is on why are the local studies on availability of crucial for bagasse ash utilization. Local studies is important for bagasse ash utilization. Why it is important? Because ensuring supply chain consistency, reduce alkalis, expedite certification, lowering cement cost. Obviously, we require consistency in the production of sugarcane bagasse ash. That's why local studies on availability of crucial is because it will ensure the supply chain consistency will get same amount of same nature of silica in it, and we require uniformity also in the production of bagasse ash. So that's why local studies are important. Next question on in a comparative carbon footprint ranking, which is the highest CO2 emitter per ton? Now we know that the lowest one is the one which we are replacing the most the clinker content, which could be LC3, PSC, or PPC, depending on the replacement level. Typically, it is considered as the LC3 as the lowest CO2 footprint. The maximum footprint is from the OPC, which is the typical cement used in the last 100 years. But there is a problem which is of CO2 emissions, hence we should go for blended type of cements. So this for today's class we have covered different type of cements, like different type of SCMs we have covered, where we have studied the sugarcane bagasse ash, fly ash, GBS, also silica fume, some of the part, and limestone calcined clay. Then there is a life cycle assessment which produces the highest CO2 emission, which produces the lowest CO2 emission, how to reduce the heat of hydration, and how to increase the reactivity of this type of cement. Also we have studied in a detail. If you have any questions, feel free to contact me through my mail IDs, or you can directly ask on the NPTEL questions. We are trying to upload all the remaining lectures over there. You can go there and watch on YouTube also. Yes. So if you have any question, you can directly ask to the NPTEL forum. I will answer there, or maybe you can mail me. That's for today's class. We have covered most of the things. Just to recap from the starting, yeah, we studied the sugarcane bagasse as Ascus cash and calorimetry, and then life cycle assessment also we have studied. Then we see that the what is that is leading to most CO2 emission, which is the clinker formation. Then we studied which is that compound which leads to most developing early strain, which is C3S. You can see it here. Then we have studied what is the reason the base explain PPC is the having lower carbon footprint. Obviously, that is utilization of industrial byproduct, which is byproduct we are using, so that's why it's having low CO2 emission. Then the problem of high surface area of Rassus cash we have studied. Then also we see that why there is excess carbon present in SC sugarcane bagasse ash, what that will lead to reduction in pozzolanic activity. Then the test done to measure identify the heat release during the initial reaction is the calorimetry. Then also we have studied the control burning reduces crystalline silica and carbon content. We can only use 20% of silica fly Rassus cash, because after that the water demand increases very high. And the sulfate resistant cement, and where it can be used, obviously marine structures where there is a attack of sulfates from the seawater is also possible. Then this was not the question for this content. Then we studied which indicator reflects the sustainability. Obviously that was the apathy index. And then we have studied what is the impact does the high alkalinity leads to in a concrete, increases the risk of high alkali aggregate reactions, how to increase the reactivity of the fly ash by grinding with the least amount of energy requirement. LOI rises as increases the temperature because higher potassium tapping in urban carbon. Then also we see the cement, white cement is used for decorative appearance. Low heat concrete is generally you make from low heat cement, which is made from using SCMs. High aluminum cement is used for heat resistant structures at very high elevated temperatures. Then gypsum is used to prevent flash set. Then C3S is used, sorry, C2S gives the late strength gain of hardened cement. Then, which is the direct consequence of clinker factor reduction, obviously lowering CO2 emissions, and the local study is required for bagasse to make it a consistent product. And which one is having highest production of CO2? Obviously OPC. Yeah, that's for the today's class. We'll meet next class next week, same time, same place. Thank you all for joining. I will close the meeting now. So we have completed today's live session. If you have any questions, you can go through the live recordings, which is will be uploaded on the YouTube, and you can ask questions on NPTEL discussion forum. So we are closing today's live session, and we'll meet uh, for the next live session next week, Monday, 6 o'clock in the evening. Thank you all for joining.